In our last chapter, we were working on linear equations and their graphs, and we found there were a number of ways that we could graph a function. Now we're going to take this a little bit in reverse, and we're going to be writing the equations. We're going to be looking at graphs, we're going to be given certain information, and we're going to be asked to write the equations initially in slope-intercept form, and then we'll explore the point-slope form and standard form as well. So our goal in this section is to use the slope-intercept form of a line y is equal to mx plus b to write the equation. We always start off with the simplest, and the simplest are when we're given the information we need. Well, it's called slope-intercept form of a line, and we need just those two things, slope and the y-intercept. Slope, we know, is represented by the variable m, and the y-intercept is represented by the variable b. If we are given those two pieces of information, we have exactly what we need in order to to write this line. So let's do a couple of examples together. Given the slope and the y-intercept, let's take the model y is equal to mx plus b and replace in what we know. We know that slope m is equal to -2. We know that our y-intercept here is 5. Given the information, replace it into the equation. Y is equal to 4 times x. Don't forget that x. This time, my y-intercept is -3. Thinking back to the last chapter, you would graph your y-intercept and use your slope to find additional points. Here we have the slope and the y-intercept again. Y is equal to 3 over 2 times x minus 1. The slope in the next problem is 0. Now I don't have to write 0 times x because 0 times x is just 0. So this becomes a constant. Y is equal to 4. And we saw that when we graph and we have y is always equal to 4, we will have a 0 slope and it'll be a horizontal line. In the next one, our slope is -3 and our y-intercept is 0. That is a model of direct variation because the y-intercept is 0, which means it will cross or pass through the origin. We start off always with the easiest. Let's now take a look at writing the equation of line when we're given a graph. So given the slope and y-intercept, just replace them in. Here, I need to identify or find those two pieces of information. I need to know my m, and I need to know my b. Well, we can easily find the y-intercept because that's a point that falls on the y-axis. So let's just count up 1, 2, 3, 4. My y-intercept is 4. I know that my slope is a ratio of rise over run, and we can identify the slope by counting boxes, which means we're going to find points that fall at a particular juncture here. So we know slope is constant, so I can go from this point perhaps to this point, and I can count up 1, 2, and over 1, 2, 3. And there is my positive 2/3 ratio. Slope is constant, so I can go again 1, 2, 1, 2, 3. All of these points will be up 2 and over 3. So we've identified those pieces of information. Next, let's write the equation. Y is equal to 2/3 times x plus 4. One more. We need to identify our slope and our y-intercept. Our slope again is positive, it's going uphill. Our y-intercept is right here, this point on the y-axis. Let's count down 1, 2, 3, -4. My slope from this point to another point, counting up 2 over 1, up 2 over 1, it's a positive 2. Now that I have my slope and my y-intercept, I have my equation. Y is equal to 2x minus 4. Think back in reverse. We first graphed our y-intercept -2, then we counted up 2 over 1, and we got our graph. Okay, so we're just doing what we learned in chapter 4 in reverse so that we could write the equation. Now, thinking about writing these equations and looking at graphs, you're saying, well, will I ever really use this? Well, when we do certain types of investigations, we can create a graph in order to get a picture of seeing change over time, which is slope. So a linear model is just simply a function that's used to model a real life situation. In a linear model, m is that rate of change, which is our slope, and b is the initial amount, which is a constant. Linear functions can approximate, for example, population change. We're going to write a linear equation to approximate the expected population change of California in any year between 1990 and 2005. A little history lesson here. California had a population of about 29.76 or 29.76 million. And during the next 15 years, the state's population was expected to increase by an average of 3,100 million per year. That's the given information. We're going to use the equation to predict the population in 2005. So we know that we're going to take the population plus the increase per year times the number of years. So we've already been given the population. So now I'm stating the given. We know the increase per year, and we know the year, we have to calculate the years since 1990. So here we have our population. We have our rate of change and the time. Well, the time from where did we start off with? 1990 to 2005 is a change of 15 years. So now we can replace 15 into the model and calculate the population in 2005. And I'll leave you to do that. But this is where you can see the connection of why we're learning certain things and how we can create this linear model to do predictions and to calculate things in real life. At the end of every lesson from now until the mid, and here's actually, I put together a rough sketch of the graph showing that there's going to be this steady increase. And again, taking it to the graph form, I didn't create a coordinate plane because I only needed a partial plane here, and I have my 0 and I set up my scale. And we talked briefly about setting up graphs earlier back in, I believe, chapter 1. At the end of every lesson this week, I'm going to do a little review topic. Today's review topic is function notation. We were given linear equations in our previous chapter, y is equal to 4x plus 1. And we were told that we could write it in function notation by replacing y with f of x. So then we can then calculate for a given point. So given y is equal to 4x plus 1, replace that with f of x, and now we're going to take and replace x with -7 to evaluate this function. And we'll get -28 plus 1, which gives me -27. So when I input -7, my output is -27. In a second equation, I could start off with y is equal to x plus 3, write it in function notation, or maybe already be given in function notation, and we're asked to evaluate. We then replace the value for x and simplify. Remember, this is just the name of the function. It has nothing to do with the calculations. It's telling me that I input -8 and my output is -5. And that's just a short review of function notation.